it's time. Let's go ahead and start, and welcome back to yet another episode of Intro to Computer Networks. And the topics we're going to talk about will be to conclude IPv6, and hopefully we also conclude Chapter 4, the data plane of the network layer. And let's see if we could just start the control plane of the network layer at the very end of the lecture today. Okay, now IPv6. So yesterday we finished talking about the idea of having IPv6 and the IPv6 packet format, particularly the network layer header. We see that it's quite different from IPv4. Now, this remaining part of IPv6 is more to talk about. Hey, we've been using IPv4 for like decades, okay? And now we have a newer version. And how do we move from the older version to the newer version? Okay. And that technique is called the IP tunneling. So this topic is a little bit special, okay? We will be talking about how we move from an IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to a version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, it's called tunneling. Okay? Establishing tunnels between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay? So this router will also be doing this. Okay? Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right? So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc., etc. Now, IPv4 packet here, coming from the border of IPv4 and IPv6 connection, is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4. And that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to N. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. An IPv6 packet here will travel through the version 6 space, but as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay? So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay? The other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. Then the IPv4 network is capable of forwarding this packet over, okay? At least to E. So E is going to receive the packet next, and being the border router, okay, being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receive the packet that is supposed to go for F.
All right, so that's a cool idea, isn't it? An IPv6 router doesn't recognize IPv4 address. Similarly, IPv4 router does not recognize IPv6 address. So how do we get around this problem? If we are sending from IPv6, we'll be generating packets with destination address looking like IPv6 address, right? But as we are crossing the border from IPv6 to IPv4, that border router there, okay, can encapsulate the original v6 packet into a v4 packet. So we add an extra header, and the destination being what IPv4 address format, then this packet can then travel the IPv4 space. So we just need to set the destination address to the address, the IPv4 address at the end of the tunnel. Then packet will reach the end of the tunnel, and that border router there extract the IPv6 packet out of it and send it down further on the IPv6 space, no problem, right? So you get v6 packets to travel through v4 space by encapsulating into a v4 packet format. And then at the other end, extract IPv6 and pass it further down. So that is this technique called tunneling. Okay, this is actually quite useful. You might see the same technique being used in other places as well. There's just one more video before we do quiz 35. And this is about what is the adoption rate? So how big is the IPv6 space? And how small is the IPv4 space? Right? We are now migrating from v4 to v6. Which one is bigger, really?
Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, pretty low. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings, okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app?
Okay, so before we talk about why, 2 points I want to stress. First of all, you see that, hey, at the client end, right, at the host end, we have progressed a lot with all sorts of applications, and new forms of applications are rising as well. But it's so hard to change these router devices just to move from IPv4 to IPv6. So that probably will convince you better, right? At the beginning of the course, beginning of the semester, we said that there's this principle of designing the internet. We leave the complexity at the edge. We leave the complexity at the end systems or hosts. And not to have complexity in the core of the internet, because it's super hard to make changes in the core of the internet. And second point, which is more to update, because on the sites, Polly was speaking in the video, there are only 8% of nodes being upgraded to version 6. As of March 2022, if you look at the upper right box there on the screen, you see that as of March 2022, which is more up to date, I think the adoption rate globally much better, 34% as opposed to 8%. So I would say that the growth is pretty fast. So that 8% was probably back in 2020, late 19, early 20. And within 2 years, we've grown from 8% to 34% adoption rate. Okay, and in US, seems to be better generally than the other areas of the world. Okay, and now let's figure out why it's so hard to make changes. Because after all, on the internet, the ones who are making the changes are human beings. So it has something to do with how human beings making changes and how hard sometimes it's to have human beings making changes. So that is that I would like to embed that discussion into quiz 35, making changes. Okay, so nothing technical here. So I'm asking you first, have you ever thought about making changes in your life? So very general, if you can think of anything. Q2, if yes, did you end up making the changes? Okay, a lot of times you thought you want to make a change, but you didn't make the change. Okay, now in case you're lucky, you made the change. Was it easy? Well, in case you did not make the change, why not? Okay, so any change you tried to make previously, did you make it or not make it? And why did you make it and why not you didn't make it? Why you didn't make it, yeah. So this is supposedly easy question, but I guess you might need still a little bit of time to think about. So why don't we spend some 5 minutes? Okay, so, and hey, there's no need of having a team discussion. Of course, if you want to have a team discussion, that's great. Okay, feel free to write based on your personal experience as opposed to a team's experience. Okay, now let's start. 5 minutes. All right, so yeah, I see you guys start telling the changes you want to make that are hard. Okay, so Team 14 here saying, try not to be procrastinator. It's hard. I guess you didn't make the change, Youyu. Yeah, it is hard. It is hard. Oh, okay. Yeah, so I kind of posed the question there to Team 14, and Team 14 is answering. Yes, we often overestimate our own working efficiency and choose to do things later. Yeah. Yeah, so we are oftentimes optimistic of how much work we can handle. Or we are already stressed. So mentally you resist to do more work because if we are already under stress, doing more work make it even worse. And you might get ill mentally eventually. So I think the real cure of trying not to procrastinate is to try to know better about using time, know better of ourselves, and know how much we can do and how much is what's the capacity. All right, so I have Team 1 saying, try to exercise daily. All right, at the beginning it's hard, but eventually it becomes a habit. Okay, that's nice. And Team 7, oh, you always want to stop playing a game and probably your best favorite game, but still haven't succeed. Ouch, because it's really interesting. I understand. Yeah, the games comes with much better graphics, and the rules of playing the games you know very well. You have no trouble, and you don't have to really, have exercise critical thinking. Although in some of the strategy games you need to, but usually in the strategy games, after you play for a while, you know what the strategy options are as well. So I think playing games a lot of times they are more entertaining than as a learning platform. Yeah. Okay. And usually when things that are entertaining, it's hard for us to stop from doing more because it's fun. But we also have this issue that we just need to do serious work as well as we have fun. And how do we keep a good balance there? So I think in human beings there's also intuition as well as ration. So ration is the thing that you don't judge things, or you try to take your thoughts deep, okay, and make a decision and tell yourself objectively what's the right thing to do. But intuition is you don't think all that much, and then you are easy drawn to things that are appealing to you. So that intuition sometimes is also called desire. Yeah, so hard. So I guess the trick is probably to get used to not making decisions all that fast. Think a little bit more before you really take actions. So that was Team 7. I think this is very honest. Okay, very honest. I would say yeah. Okay, for quiz 35, a very good answer there. Team 2, yes, I wish to spend more time exploring different things. Aww, same as Polly. So that's why Polly can't wait to have the summer break. That's usually the time Polly can think a little bit more wildly and learn things that are different from computer networks. Unfortunately, no, I'm sorry. Still trapped in homeworks and tests for now. Yeah, but Zhaoqi, I guess you are also looking forward to the summer. Okay, love it. 冠语, let's see. Oh, get a driver's license. Okay, that's I know in US that's the first step towards independence. So getting a driver's license, it means a lot, okay, to a young adult. Not yet. I'm just kind of lazy, and it doesn't seem to be too necessary if you live in Taipei, right? Yeah, I think so. Interesting, very interesting. But in this case, you did not make it, not because it's hard. It's interesting in a way that you thought that you need it because everybody says so. But to you, it's not exactly all that important. Therefore, you delay doing it. Okay, very interesting. Very interesting. Okay, I guess it's a little bit like migrating from IPv4 to IPv6. If you think of it, it's not that hard, right? They just need to turn off the router and upgrade it to a different OS version, or purchase a new router that is, supporting IPv6 with sufficient efficiency. Okay, or purchasing a router that can interoperate IPv4, IPv6. Okay, it's probably not exactly hard to upgrade a local area network or a network domain to IPv6 capable, but for some reason, people are not doing it. Probably because you can do away with just using IPv4 anyway, right? Even people who moved already to IPv6, they still need to worry about communicating to IPv4. They always try to make sure that they can they try to be backward compatible to IPv4, and therefore sticking to IPv4 will still work. See? There's no need. Okay? I mean, desperate need. 关于 you might want to try living in US, particularly California, without a driver's license. You'll constantly be begging people to take you places. So, hey, try travel to US in summer, 关于. Let's see, Cai Tong, Team 3, yes, try to get to bed early. Yeah, I think this is one of the top issues that you want to make changes as well. Playing on cell phone and falling asleep. Yeah, so you're already laying on the bed, but you're still, looking into interesting things that you can see from the various apps on your smartphone, isn't it? Very common. Let's see, Jason. Yes, but only some of them. So I was actually asking more, what is the theme that you're trying to make a change? Not yes, whether you have ever experienced something like this. Yeah. So I see that the statement below is generally it's very general. Yeah. Let's see. Yes, try to make notes and take study plans. Okay. Howard. You are trying to be disciplining yourself. That's good. No, it only lasts for one semester. Ouch. Okay. I guess if the course load is too high, then it's hard to do this, right? It's hard to keep working hard. But Howard, I don't know if you have discovered. So the longer I keep trying, even though that I don't make it every semester, okay, I do not hold the plan. I do not get through the whole plan every semester, but every semester I get to last a little bit longer. Okay. Howard, have you tried running the marathon? Or, long distance, something like 10K, 5K. You will see how you eventually can grow to make sure that you're disciplined for multiple semesters. You can run a long distance. It has a lot to do with how to find your pace. Okay. Team 14-2 anonymous. Ouch. Okay. Oh. Oh. Uh, I'm here by far since I don't know what I want to major in. Okay. Okay. Yeah, so you doubt. You doubt. Maybe I should change the major. But you didn't make the change. Because you don't know whether which other major to change to either. Ow. Okay. I know it's hard, but I think the way to start is to try to take courses, uh, essentially the required courses in the other majors, okay, and see what their fundamental courses are like. Usually, you can find fun courses from the other departments that you can take, okay, but that's just one aspect of that particular discipline. It's not the whole thing. I don't know if I'm really in position. Polly is not sure if she is in position to come in, but Polly often finds that each major, I kind of like it in certain subjects, but not the other subjects. So Polly has majored in math in college and majored in CS in grad school. And then my first job, I started working in an EE department. Okay, so in the end, I decided to stay in EE. Okay, but with a little bit of randomness. Okay, and now I kind of appreciate some of the subjects I study in each of the majors, but not all the subjects in each of the majors. Okay. Very interesting. Whoever the anonymous contributor is. Yes, try to sing better. Oh, draw better, code better, and faster. Jogging or swimming every day. You know what? Sleep well, do better. Wow, there's so many things you want to change. Master more languages and play more games. You might be thinking like Polly. Polly often finds that time goes really fast. Yeah. Regretful, none of these is easy. To be easier, even playing more games might get short of time of other tasks. Yeah, so I guess the problem here is more that you want everything and you cannot have everything. Yeah. Oh, I know. Okay, I don't know if Polly has complained. I feel that the money is not really is not the resource that's scarce. Time is the real resource that's scarce. It only get less instead of more. Money you might be able to earn gradually more, but time you just run out of it. It never get longer. Sorry, I don't mean to depress you. Yeah, so enjoy every second of it, definitely. Thinking that way, right? Knowing that way. To get up early, yes, as long as I go to bed early. Jia Hong is very disciplined, I can tell, because you are always the first one greeting to Polly. Even on Wednesday, the morning session. Yeah, I know. You got you get the trick of getting up early. Okay, Jia Hong, definitely try to share with the rest of the class how you made it. It's hard because I think I just saw Cai Tong said it's hard to get to bed early. Cai Tong, definitely get Jia Hong and ask how he managed to get that changed. All right, so quiz 35. Although that you guys responded in very interesting ways with diversity, but the point is to say that when changes involve human beings, a lot of times it's not that easy. Okay, And you see some of the reason is that if you don't make changes, it doesn't hurt. You can still live on. You live on, yeah. And even if you make changes, yeah, you feel better, but a lot of times you don't necessarily see that there's a clear change, okay, until later. All right, so that was the end of IPv6. That was the end of the traditional forwarding. And now we go on and talk about the modern forwarding, okay? And if you still recall, in the beginning of the chapter 4, it's called the generalized forwarding. So here, the decision of forwarding a packet is no longer just based on the destination address. It can be based on destination address and the source address, and the destination port, and maybe the MAC address. Okay, so the matching rules are more general, no longer very specific, just the destination address. So here's the overview video.
Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, yeah, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. Now, if we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. So in the traditional forwarding, yeah, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now, the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now, if you recall the overview of chapters 4, you should recognize in SDN, the control plane looked very different. And instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finished computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, okay, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. Okay, so we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, okay, and then determine it should go out on interface 2 arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, okay, matching the destination and source address. So in the header column, okay, of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry, and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose, last column here for action purpose, and counter here for management purpose.
All right. So from the video, you see, hey, generalized forwarding is not just that you match entries in the header fields, not only match fields in the header, in addition to the destination address, you could have other fields that you want to match. In addition to this, we can actually take actions, that's not just forwarding. We can actually take other actions as well, such as drop, and we'll talk about in the next video. And it also account the packets matching specific rules. Okay, so generalized forwarding is more than just traditional forwarding in terms of how you do the matching, but also taking actions and taking a control or monitoring. Next, OpenFlow. This is the protocol that allows the control plane to install these rules in the flow table.
To put in simpler words, we take a combination of these header fields with specific values, and we define that as a pattern, okay, for a flow. So whenever there is a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table. Some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances is actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority, therefore we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. Then, you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the length to break the tie. So we have a specific priority field there to break the tie. Okay, so the for table in the router, for column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2. something. So the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then it doesn't matter what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4. something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. This is the data plane abstraction for SDN routers, all right. What does OpenFlow mean? OpenFlow, capital O, capital F. It's a very specific term. It is the protocol defined for communication between the data plane router to the control plane remote controller. So the remote controller installing forwarding table using the OpenFlow protocol.
All right, so now you see that how these rules in the flow table can be very, very general, not just in the matching rules, but also the actions. And you see also that there's also priority that people can set to the rules. And next, let's dig into further and check out the flow tables, the structure, the entry, how they look like more precisely.
With the generalized forwarding explained, now let's go back to this notion, the flow table. This is one of the most important things in SDN's data plane. Recall early slide, flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column, priority, and we just ignore that here, as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters, we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward a packet to an outgoing interface, one can forward a packet to the remote controller. One can drop a packet as an action, one can also change the content of the packet as an action as well. So, all these, straightforward. Now, this column here, very complex. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early slide is also called a header column. The reason it's called a header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets coming into the router through a particular incoming port. So that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. So that's also why in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general.
All right, so that should give you a clear idea how an entry look like in the flow table. So Polly has been saying that the general forwarding can look at the header fields in different layers of headers. But you see also that the input port, the switch interface, that is not exactly in the header. It's actually just how the routers can tell the flow table that this packet coming in came in from a particular interface. So that requires help from the router itself. Okay. All right, so it's a good time to take a break. We'll resume the lecture. There's another video about flow table we have not yet complete watching. In that video, we'll see examples, okay, setting up rules in flow table for different purposes. You can actually set up these rules not only for routing, forwarding purpose, but also other purposes. Okay, so it's actually really nice to purchase an SDN router because although it's called the router, the way it works that you see that you can change packet headers as well. It's a device that's even more general than net boxes or net software, that you can actually change headers in all the layers. Okay, very, very flexible, very, very general. Okay, to some people, it's no longer a router. Right, so break, and we'll resume at 11:20. right, welcome back. Let's now check out a few examples that's using OpenFlow to set up these generalized forwarders to do other things.
Let's take a look at how diverse these rules can be, again through a number of examples. First is the destination-based forwarding. And this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. Okay. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet definitely, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A min or a root username and guessing the passwords for the root or a min. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. Okay. So blocking packets to port 22 is to block any logging request to port 22. Therefore, SSH is disabled on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack. DOS attack, denial of service attack. You see, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share IP addresses of zombie machines. So if one day a hacker hacks through the workstation and take over the workstation, 140.112.42.161 is going to be a zombie IP address. So the experienced system admin, after looking up the website displaying all these zombie IP addresses, can set up these entries with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in and asks all the zombie machines to issue, for example, login requests. Then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address and the link layer. That is also called the MAC address. and it look very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right?
So that's how the SDN forwarder or SDN router can be used not only as a forwarder, but also as firewall, as a link layer switch. All right, and now comes quiz 36. Okay, so we have 3 devices. Okay, on the left you see that there's a laptop. The IP address is 36.227.4590. And then there's some sort of server. Okay, in the middle, 140.112.2.110. Okay, and then in the end, there's yet another server. Okay, 140.112.42.221. Oh, hey, that was the IP address of the workstation we have, right? So obviously, a client with IP address 36.227.4590 wants to access the workstation. But there is a flow entry in the laptop that look at the source IP address, okay, the source port number, and then change the destination address and change the destination port number. And such that these packets will go where? Go to the middle machine, right? Obviously looking like a server. And there's a entry in the flow table of the server machine in the middle, 140.112.2.110. It will match the source IP address, source port number to the laptop. If that's the case, they changed the source IP address, destination address, source port number, and destination port number to something different. The source is changed to the server's IP address, no longer the laptop's IP address. Port number is changed to the server's port number as well. And destination address is changed back to the original destination, okay? 221, accessing the workstation. All right, so first entry there is installed in the laptop. Second entry is installed in the server in the middle. Okay. Question is, what do you think these 2 entries are for? Okay. Now this one is a little bit challenging. Okay, this one can be very challenging for some of the teams there. Okay, so let's give it some 7 minutes. And for this quiz, the fastest correct solution gets the bonus. All right, 7 minutes. Start counting. Okay, so I obviously underestimated you guys. Yeah, so Team 5 here gave the solution within like not even a minute. Client wants to connect to the workstation's SSH, but the client connects to the VPN server first, and VPN server forwards the connection from client to workstation. Yeah. But hey, for those who are looking to also earn bonus. Think this. What will be the entries like for the returning packet? So there obviously needs to be another entry, right, at the server, the VPN server, to make sure that the returning packet will get back to the laptop. Yeah, so is there an entry needed? Actually, there's also an entry needed here, okay, from the workstation, so that the packets will go, wait a minute. I think only an entry is needed for the VPN server to ensure the packets returning will arrive at the client. Okay, arrive at the laptop. Yeah, so if you can come up with the entry, type it up, you get the bonus as well. Okay, so I think there's 4 minutes remaining. And of course, Team 5 can also get the second bonus. Okay, hey, that's Polly is now thinking what entries should be in the server, the VPN server, and whether there are entries needed at the workstation or the host. All right, so hey, time's up. Oh, okay, first connect. Okay, I see Ke representing team 10. Connect to VPN at port 1194. Then forward to the workstation at port 22. Okay, so, yep. So this is these two entries setting up at different places are for VPN service. Yeah. Okay. Yeah, if you look at what VPN server is doing, it's actually working a little bit like the NAT, isn't it? Yeah, so changing the source address, okay, for packets going out, and then changing the destination address for the packets coming back. All right, so I guess, yeah, as I said, it's challenging. I'm totally surprised that Team 5 solved the problem all that fast, but you get the idea. Okay, so you could use the flow tables, or you can configure SDN forwarders to be an array of network devices. And now let's move on. Okay, so from quiz 36, you see that hey, you can have these entries at different machines on the network. So let's check out a complete network example, having routers that do generalized forwarding.
With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. So you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the OpenFlow protocol. Right? So this controller here sometimes being also called the OpenFlow controller. Just like the SDN routers, okay, some of them will actually call them the OpenFlow routers. A scenario is this: let's send packets from H5 and H6 here and here. Okay, from subnet 10.3 to H3 and H4. H3, H4, subnet 10.2. Okay, but through a very specific route. Okay, from S3 here through S1 and then reaching S2. So we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this. Okay, if you want to send data from 10.3 subnet to 10.3 subnet. Because this is only one hop, okay, this is the shortest path. Traditional routing does not provide you the flexibility of manually configure a specific route. But hey, luckily we have the OpenFlow controller. So OpenFlow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, S2. And these entries will look like this. Okay, inside S3, the flow entry will look like this, source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now, the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 for entry, looking like this. Increase port being 2. Yeah, so packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there, I got this one. On the other hand, if it's 0.4, then forward it on interface 4, therefore reaching H4. So open flow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? Yeah, the controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing.
All right, so that was a full example. So you see that inside the flow tables on different routers, you can set up entries to enforce packets to go certain direction, certain routes. Quiz 37 is asking you to exercise what you just saw in the example. You see that the network here is identical to the example in the video. Okay, Q1 asks, which way would traffic go from host H5 to H4? Okay, so this is a very straightforward question. Q2, suppose H4 needs to send traffic to H5. Okay, so H5 to H4, that's a pass going forward. And then there'll be some packets that need to return from H4 back to H5. And we want to enforce H4 send traffic back to H5 through the B network. H4 is where? In the C network, right? I think it's the host on the, that's the rightmost in the network. And H5, where is it? Okay, it's in the A network, but the one on the left. Okay, so H5 sends traffic to H4 through a certain path. Tell me, that's the answer for Q1. Q2, can you add entries to the table? Okay, it can be C's table or B's table or A's table or all of them's table to enforce that packets can come back from H4 to H5 through router B. So that's Q2. All right, and for this question, it's also the fastest response gets the bonus. And there are multiple ways to set up ABC routers to get Q2 to work correctly. So you don't have to worry. So try top 3 fastest that are working and not identical gets bonus. So let's assign 7 minutes. How about that? I think 7 minutes usually because I thought it's challenging, but you guys might came up with the answers faster, so surprise me. Okay, so 7 minutes, start counting now. so now let's check out the solutions you guys have typed up. I think some will work in case other nodes are not sending other traffic. Okay, but if other nodes might also be sending other traffics, you want to be careful. Let's say, okay, I think Team 3 is still editing the solution, so why don't we let Team 3 some time, allow Team 3 some time to do the editing. Let's start from reading Team 15's solution. So for Q1, A, B, C, yeah, that's what the table says. Okay, so I think Team 3 also get it right. But I think the key question is Q2. So Team 15 is saying that at router C, in case the ingress port is 4, forward to 2. Oh, what does that mean? In case the ingress is 4, forward to 2. And this is regardless of what the source or the destination IP is. Well, actually, no. Ingress for interface 4, the source must be 10.2.2.1, must be H4. So this rule is fine. Okay, and it will go out to 2. Yeah. This rule set up at router C, no problem. But you see that in case H4 sends packets to other nodes, but H4 might prefer, for example, sending from C straight to A instead of B, A, then that setting will have an issue. So you see that H4 to H5, okay, using this entry, if H4 sends packet only to H5, then this is fine. If H4 sends packets to H6 and H4 would like to send it just CA directly to H6, this entry will be an issue, right? And for B, ingress being 4, forward to 1, I'm thinking that Team 15 is assuming that the only traffic is just from H4 to H5. Okay, in that case, yeah, sure. At B, take packet coming from ingress port 4, forward it to output port 1. Okay, and here, from ingress port 3, output to port 2. Let's see. Yeah, 3 to 2, 4 to 1. Okay, I think that's what Team 15 was saying. In case there are no other traffics on the network and there are no other specifications one might assign, then this is fine. But in case there are other specifications, other traffics, then this is probably a little bit too general. Can you come up with a set of rules that will always be fine, okay, and allowing other rules being set for other traffics to go? So let's see Team 5. Team 5 says at router A, ingress port 3, source being 10.2 star. That means I think that means H3 and 4 traffic. Okay, will all be accepted, and in case the destination is 10.3.2.1, forward to 2. Would this be okay? I think it's okay, right? Because when the packet has already arrived at router A, what the sources are is less relevant. The destination is the key, okay, to decide which interface to forward to, because there are only 2 interfaces router A need to decide in case the destination is in the subnet. Okay, so this is actually good. Let's see, router B, destination being 10.3. Hey, wait a minute. Destination being 10.3.2.1. Wait a minute. 10.3. Okay, yeah, you're right. Yeah, because the cluster in the A network is 10.3.2. Yeah, so 10.3. If the source are all these, send it there. Yeah, I think this is also okay, right? Because B router there is in the middle. If the destination is for 10.3 subnet, yeah, go there. And if the source is 10.2 subnet, together, go to port 1. What about C? Destination being 10.3 action forward 2. Let's see. Yeah, so destination being here, we enforce it to go out on interface 2 so that it will go to B. All right. But I think this has an issue because we are not trying to match the source, which means H6 will also take CBA. Okay, so in case in case H6 wants to go directly from C to A, then this entry need to be changed. Okay, need to be modified. Okay. But I think the set of rules that Team 5 said is already more specific, works for many cases. Okay, except in case H6 insists sending packets through CA, okay, to 10.3 something. Okay, not bad at all. Okay, already better. Let's see. Okay, hey, so Team 12 here is a little bit stricter, right? So at router C, if the destination is this, and ingress is 4, which means the source must be H4, I think. Yeah, the source must be H4, okay? Very specific, great. And ingress port 4, destination 3, okay, forwarded 1. But ingress port 4 means traffic coming from C. I think this is okay. Yeah, I think this is okay. This is the same logic behind Team 5 setting up the entry for router B. What about A? It's also fine. Okay, yeah, this is actually perfect. Okay, no conflict, potential conflict with other settings, specific settings. Okay, great. Team 10. Yeah, so Team 10 here sets to the entire 10.2 subnet and 10.2.2 subnet. Very good, very good. So very specific. So Kuku here is, yeah, is gonna work as well. Yeah, so the more specific rules you set, the less conflicts you need to worry about later. Yeah. All right, good. I think Team 5, Team 12, Team 10. Okay. And Team 15, definitely. Okay, and Team 3 for trying, definitely. Okay. Okay, you guys will get the bonus. Okay. For the rest of you guys' entry, probably we'll take a look closer later. Okay, I guess you guys will then be more or less alike to one of the possibilities we've already examined. Very good. Here, exercise quiz 37 is to communicate one thing. Okay, you can set the rules to be general, but it will work when there's only traffic from one device to another device. If you wish that you don't need to reset the entries later on, in case there could be specific source destination pair that travels weird paths, then when you're setting up the entries, be more specific as well. Okay, good. And you know what? That concludes chapter 4. Woo! Celebrate. And we have about 9 minutes remaining. So that's just, getting to chapter 5. Let's open chapter 5 with the intro.
Chapter 5, Network Layer, the Control Plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now, the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup, and you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing is just table lookup, and it's just pattern matching. Right? But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly, trying to forward packets, but it's actually simple, stupid. Intelligence is right here in the control plane. And the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, with the right amount of resources reserved. So routing algorithm there, very intelligent. So in fact, the first part of chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about 2 general routing algorithms. So they are graph algorithms. So provided a graph, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. That is what the magic of the routing algorithms are. So these 2 general routing algorithms will be implemented on the internet as 2 routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. The control plane of each router might be communicating with the control plane of other routers. And together, they complete the task of calculating routes, and in turn, generating the forwarding table, and in turn, install the forwarding table to the data plane, and in turn, the forwarding function can be working really fast. Now, the new model of doing routing is called SDN, Software-Defined Networking. So the one that's doing the route computation is the controller. This is also known as the remote controller, because in SDN, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. In fact, powerful machines, somewhere remote. That's why these controllers are also called the remote controllers. And between the remote controllers, routing is being done where we generate the flow tables. And the CA, the control agent, now in the data plane, that's taking in all these tables being transferred from the controller. In between, there's this open flow protocol. Now you should know after chapter 4. So after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do flow table lookup, do generalized forwarding. Now, the remote controller here, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by the traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, or specify other functions. So SDN's remote controller, being very general, is actually working like pretty much a regular computer, or expensive servers. So on these SDN remote controller, we run operating systems, elaborated operating systems, such as ODL or ONOS. So these are 2 different operating system architectures, and both have big camps of supporters. So Yeah, SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay. So these protocols, as well as these two, okay, of the technical components in Chapter 5 concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management. Okay, so management of the routers or the routes or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, status of the routes. Okay, so again, for management purpose.
All right, so that was the overview of Chapter 5. But as you see on the slides in the video, Polly had some topics graying out, okay, gradually more and more. So SDN controller, we'll see if we have time to talk about them this semester, hopefully so. But SNMP or ICMP, we won't have time to talk about them. Those protocols are actually more straightforward, just to collect data about the network. So we won't be talking about SNMP, ICMP at all. But we'll be spending a lot of time talking about the routing algorithms and how the routing algorithms might be working in different levels on the traditional routing on the internet. Okay, the IPv4 is still working in a two-level hierarchy, and one routing algorithm commonly used at the lower level, another routing algorithm commonly used at the higher level. Okay, and we'll start talking about these next week. And it's already 12:08. With that said, essentially we conclude the lecture today. If you have any questions, feel free to type the questions up. And for those who have not yet completed quiz 35, 36, and 37, this will be a good time for you to try to make it up as well. Okay. And for the rest of you, no questions, have already submitted the quizzes, you're free to go. And I'll see you next week. Bye. And by the way, hope that you made the changes you want to make. Okay, eventually. Yeah, bye. Bye, 冠宇, bye, Howard, bye, 幼瑜, bye, 嘉宏. And Yu Jie and Jason, Wei Xiang. Oh, Wei Xiang is here today, okay. Yu Xiu and Amelia. Oh, good to see you as well, Doris. Yeah, bye, 赵琪. Bye, Catfish. And bye, bye, 慧心. Okay, Doris. Good that you catch quiz 37 last second. Comfort zone. Sacrifices for changes too. Very interesting. It's hard to do the hard things, aren't we? Don't we? Yeah. If you have 72 hours a day, you will have 3 times more things to do as expected. Of course. Well, I suppose this is not a question. This is more an answer. Yeah, I guess I think Keke and I meant that we would like to do a lot more things that are interesting, okay, than what we're doing now, than what we are bounded to do now. So usually the things that you find fun with, sometimes you can do it without the need of sleeping. I've seen people who are addicted to games to do that. They just keep playing and playing, and they don't need to sleep, really. That was amusing for me. All right, so hey, it's office hour, so not to stream the Q&As in the office hour out to the public, let me close the stream. Okay, so bye Youyu, bye Keke. Although you guys are having a fun discussion, there it appears. Okay, so let me end the stream.